Welcome to this lecture series in number theory. In this lecture, we'll look at two puzzles which will illustrate the unreasonable power of the Chinese remainder theorem. The statement of the Chinese remainder theorem is this. This is the general statement, and this is the special case of that general statement when you substitute n as 2. So we saw this in detail, and let's proceed. So here is a very interesting puzzle. It says that suppose we fix a prime p and some arbitrary integer a, we want to show that there is some positive integer x which satisfies this strange congruence. Right? This kind of thing we generally do not see. Not here and not in mathematics in general. Alright, so it doesn't give any clue as to what to even do, how to approach this. And when faced with such a problem in mathematics, one can always do two things. First is to experiment by hand, and the second is to experiment by means of a computer. And in the process, one observes patterns, and sometimes one discovers something which was not even asked by the question, etc., etc. So let's experiment and see where this goes. And yeah, before I start writing, I encourage you to pause the video and think about it. Right? That's kind of an essential thing if you want to take away a good deal from this lecture series. Okay, so this is how we will proceed. We will choose a small value of p. I'm choosing p as 5. And then I'm just listing out x to the power x for x starting from 1. Right? So 1 to the power 1, 2 to the power 2, 3 to the power 3, and so on. I've listed them all out. The problem says the following. I'm just restating the problem. It says that if we reduce all of these numbers modulo 5, then we will witness all the possible remainders modulo 5. That's exactly what the problem says. Fix a prime p, you can choose a to be arbitrary and find an x which satisfies this congruence. This is same as saying that all the possible remainders modulo 5 are available to you when you reduce this sequence modulo 5. Okay. But now here is the key observation, that you can reduce or you can shave off from the exponent if the exponent is big. So what I'm saying will be clear when I write the next row. So I'm just writing the above row, but modulo 5. So modulo 5, these two things are of course equal because they are equal on the nose. But here I will write 5 to the power 1. And why am I shaving off a 4 from here? Clearly these two are same modulo 5. That's not a problem because both are divisible by 5. I'm shaving off a 4 because of Fermat's little theorem. It says that if y is relatively prime to p, then y to the p minus 1 is congruent to 1 modulo p. So the exponent matters only modulo p minus 1, provided the base of the exponent is relatively prime to p. But that little leeway you may allow me, because here when we shave off, we are left with positive exponents, so it doesn't matter. Both are divisible by 5, so it's kind of silly here, but it will be more apparent as we go along. So here I will write 6 to the power 2. Right, 6 is relatively prime to 5, so 6 to the power 4 is congruent to 1 modulo 5, and hence 6 to the power 6 is congruent to 6 square modulo 5. Similarly for 7 to the power 7, so here I can write 7 to the power 3. Here I can write 8 to the power 4, 9 to the power 5, and here I will write 10 to the power, or even before I go ahead, instead of writing 9 to the power 5, I'll write 9 to the power 1. Right, because 9 is p minus 1 times 2 plus 1. Recall, p is 5. So again, it doesn't matter what is here, that doesn't matter. Since 9 to the power p minus 1 is congruent to 1, whatever you multiply with p minus 1 in the exponent is irrelevant. So I hope you follow that these two things are same modulo 5. And here also I will shave off 2 times 4 to get 10 to the power 2. Again, this is a triviality because 10 is divisible by 5. So continuing this way, here we will get 12 to the power 4, and here I will write, sorry, it shouldn't be 12 to the, is it? 10 to the power, wait a second. Yeah, it's okay, I think. No calculation mistake has happened. 4 3s are 12. Yeah. So everything is fine, I think. Right. So here I will write 13 to the power 1, because again 13 is 4 times something plus 1. So I can write this, and so on and so on. So the exponents now are coming in a cyclic fashion. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this kind of suggests itself that this linear way of writing it is probably not the best way. We should maybe make a table out of it. So what I'm trying to say is, we will copy all of these and arrange it in a tabular fashion. So these I will bring here. Basically, I'm trying to match the exponents. And so on. Correct? Dot, dot, dot. So let's just look at the first column. The exponents are all 1, so I may as well erase them. But crucially now, this is a sequence which starts at 1 and you're advancing by 4. You're starting at 1 and advancing by 4. But 4 is relatively prime to 5. And hence, this column itself will witness all the possible remainders modulo 5. Right? So, yeah, I mean, I don't know what else to say. Right, so that's it. I mean, here itself you'll witness all the possible remainders modulo 5, and that shows at least a proof in the case when p is 5, and you can generalize it to any p. The same reasoning, but the Chinese remainder theorem will pack in all this in a way that will kind of hide all this complexity or all this hodgepodgeness of this proof. Expressing this same idea in this way will require a lot of writing and explaining, but the Chinese remainder theorem makes it so simple. So let me show it. It's the same idea, but by use of Chinese remainder theorem. So consider these two congruences. So we have considered two congruences, and since these two are relatively prime, being consecutive integers, they are relatively prime, there is a solution to this. So there is an x which satisfies both these congruences. And now we claim, right? So there are two cases. One case is that if p divides a, then clear. Why is it clear? Because if p divides a, then p also divides x, because of this congruence. And if p divides x, then this is congruent to 0 mod p, and this is congruent to 0 mod p. So if p divides a, then clear. So we may assume that p doesn't divide a. And hence, in particular, or it implies that x is also relatively prime to p. So I'm not writing that, but it implies that. And now x to the power x is what? X to the power x is x to the power p minus 1 times something plus 1. Why is that? Because of this congruence, x is p minus 1 times something plus 1. Right? But now we can write it like this. And since x is relatively prime to p, this is congruent to 1 mod p. Therefore, this is congruent to 1 mod p, and all we are left with is x. So this is congruent to x mod p by Fermat's little theorem. And hence, this is congruent to a mod p. And that solves our problem. So we have expressed the same idea, but somehow this may betray the simplicity of the solution. Put this way, the solution seems to have come out of nowhere. But even so, one should realize that again, because of Fermat's little theorem, the remainder of this modulo p depends only on the remainder of the exponent modulo p minus 1. Right? Again, that's a little bit of a lie, but that's okay. So that was kind of the idea of considering these two congruences, but really this thing is what is happening in the background. All right, so let's move on. So this is also a very interesting fact. This is a problem that appeared in IMO 1989. This was problem number 5. It says that suppose n is a positive integer. We want to show that there exist n consecutive positive integers such that none of these consecutive integers is a prime power or a power of a prime. So previously we have seen that you can always find for any n consecutive positive integers such that none of these is a prime. That we have seen, and we rendered it as saying that there are arbitrarily large gaps in primes. What this problem is saying is a little bit more general. It says that there are arbitrarily large gaps in the set of prime powers. So it is certainly a stronger statement, right? Okay. So yeah, now again, I encourage you to pause the video and think about it. It's a very interesting fact. It's a very meaningful statement. All right. And again, whenever we are faced with a problem, one can always do the following. Not always, but most of the time one can do the following. Solve a simpler problem. This problem is a hard problem, naturally. It's from the IMO, so it's not supposed to be easy. But we can always think of a simpler problem. So let's go back to the basic statement that you can always find n consecutive positive integers, none of which is a prime. Forget about prime powers, right? And let's see how we may prove it. We saw a proof of it, but let me show you a proof of it using Chinese remainder theorem. It's going to be very silly, but it's okay. So here is a proof of the basic problem using Chinese remainder theorem. So what do you want to do? You want to say that there is some integer x such that none of these n numbers is a prime. This is exactly what you want to say. I'm talking about the basic problem, not this problem, right? I'm just concerned with showing that there are n consecutive positive integers, none of which is a prime right now. Okay, so we want to find some x or show the existence of x such that none of these is a prime. So what's a way to achieve that? We saw one constructive proof last time, or previously, not last time, but at some point. But how do you ascertain if something is not a prime? Just show that it has a divisor. If it has a non-trivial divisor, or let's say, suppose it has a prime divisor, then it is a prime unless, it is not a prime unless it is equal to the prime that divides it. That is a tongue twister. What I'm saying is, suppose I know that this is divisible by 5, and I also know that this is greater than 5, then it cannot be a prime, right? As simple as that. So fix some n distinct primes. Fix pairwise distinct primes p1 up to pn, and demand, or rather form, these congruences. So first congruence is x plus 1 congruent to 0 modulo p1. Second is x plus 2 congruent to 0 modulo p2. And so on. X plus n congruent to 0 modulo pn. By the Chinese remainder theorem, there is an x which satisfies all of these congruences. Further, there are arbitrarily large x's which satisfy each of these congruences, simply because once you have found one x, you can replace that x by adding to it the product of all these guys. That's a triviality. So there are arbitrarily large x's which satisfy each of these congruences. In particular, you can find an x which satisfies this thing, or I should say, yeah, I think maybe I can just write this much. Let me write it in a slightly convoluted way. X plus I is greater than pi for all I. So what I'm saying is that there is an x which satisfies all these congruences simultaneously, as well as these inequalities. That's simply because you have arbitrarily large x's which satisfy each of these congruences. Now, once we have such an x, this cannot be a prime. Why? Because what I'm saying is that this cannot be a prime because it is divisible by p1 and it is greater than p1. X plus 1 is greater than p1. Correct? Similarly, this cannot be a prime because it is divisible by p2 and it is greater than p2. So none of these are primes. So Chinese remainder theorem proves that there are arbitrarily large gaps in primes. Now we'd like to kind of maybe salvage or adapt from this piece of reasoning to address our general concern. Okay, how we may do it. So I want to now show that this cannot be a prime power at the same time. Like there cannot be any prime whose power is equal to this. So what do I do? Maybe if you just worry about it for a small amount of time, it will occur to you, just show that it has two distinct prime factors somehow. If this has two distinct prime factors, it cannot possibly be a prime power. Think about that statement. And now once you have that insight, consider these things. Consider 2n distinct primes, p1 q1, p2 q2, pairwise distinct, and also consider these congruences. X plus 1 is divisible by the product of p1 and q1. We want it to have two distinct prime factors. X plus 2 is congruent to 0, what have I written? 0 modulo p2 q2 and so on. Right? By Chinese remainder theorem, there is one such x, because these things, they are pairwise relatively prime. Since these are pairwise distinct primes, p1 q1 is relatively prime to p2 q2 and so on and so on. So there is one such x. And since this has two distinct prime divisors, this has two distinct prime divisors, this has two distinct prime divisors, none of them can be a prime power. Impossible. That's it. Such a short, sweet solution to a very meaningful and difficult looking statement. Okay. But before we go, I would like to give you an alternate proof of it, which doesn't use Chinese remainder theorem. Right? So I think this is an official solution present in the somewhere, some database somewhere. I think these are supplied by the IMO itself. But this is not the way I did it. I had a different thought, which works, but it's a little messy. So I will illustrate the idea via a simpler statement. We want to show that for each positive integer n, there exist n consecutive positive integers, none of which is a prime or a square of the prime. So this is a slightly weaker statement, or you could say very weaker statement than the one that was asked in the IMO. But once you see the proof of it, you can easily conjure up a proof of the general statement. So let me try to explain. I don't know how well I can do it, but let me try to explain this. We already know that there exist large gaps in primes. So choose some large number n, and we have this set of n positive integers consecutive. None of these are primes. So none of these n numbers are primes. And this looks like a continuum, but I just meant to say that there are capital N positive numbers here, where n is large. Whatever large means, we will decide that later. So let's say this endpoint is x, then we have x plus 1, or maybe let's start with x plus 1, that's more convenient maybe. And here you have x plus capital N. Okay. So none of these are primes, but the problem is some of them may be squares of primes. Who knows? That's a possibility. So let me try to count how many of them are squares, period. Let me forget about prime squares. Let me try to see how many of these can be square of anything. Square of any positive integer. Now, starting from 1 up to x, there are how many perfect squares, right? We are talking about perfect squares. We are just trying to count how many perfect squares are here. So we may do it by counting the total number of perfect squares up till this point and subtract from it the total number of perfect squares up till x. So the total number of perfect squares that are there, or at most that are there, is this. In fact, it's almost exact. Right? I mean, there is some irrationality business, but roughly this is the correct answer. Maybe a count of plus minus 1 is needed. So this is the total number of perfect squares that are present here. Right? But it should strike to us that this number is very much like square root n. Let me justify that. So this number is equal to, I will divide and multiply by square root n. When I say n, I mean capital N, as I've written. So this is equal to square root n. And here we will see 1 plus square root of this number minus this thing. And this cannot be a big number, right? You have some number, whatever this might be, you take the square root of it, or you take the square root of 1 plus it. This difference cannot be big. And a very easy argument shows that this is at most 1. So we can write that this is at most root n. Right? This cannot be greater than 1. This is at most 1. Yeah. So the number of perfect squares within this region is very small compared to the size of this region. The size of this region is capital N. But there are only root n many perfect squares. So there should be a gap of at least root n by 2 somewhere in this chunk where no perfect squares occur. Since there are very few perfect squares here, there must be a big gap between some two of them. Right? Because if every small gap contained a perfect square, there would be too many perfect squares. So one bad bound, one bound that works but not the optimal bound, is as follows. One can find there is a chunk, there is a consecutive chunk of size at least root n by 2 with no perfect squares in the above. In the above segment, with no perfect squares and hence no perfect prime squares, with no prime squares, with no squares of a prime, which do not have any square of a prime. Since no perfect square occurs in the chunk of this length, no prime squares occur in the chunk of this length. So why is that? Well, if every chunk of this length had a perfect square, then you partition this thing in chunks of size root n by 2. How many such chunks are there? There are at least 2 root n such chunks, right? N divided by root n by 2. At least those many chunks are there. The only problem is that these are integers, so there is some plus minus 1 business. But anyway, roughly there are going to be 2 root n chunks. And if every chunk contains a perfect square, there would be at least so many perfect squares, but we already have bounded the number of perfect squares by this number. All right. So if we choose capital N as a large number, suppose we could have chosen capital N as any number we wanted. If we just choose capital N as 4 times n square, then we see that there is a chunk of size n here somewhere which does not feature any perfect square. So these n numbers, none of them are prime because none of them are prime. So these n numbers, none of them are prime and none of them are perfect squares either, and hence none of them are prime squares. All right. So that's great. So this piece of reasoning, if you just bump it up a little bit, you can prove the general statement. In fact, it proves a little bit more than the IMO problem demands. It proves that the set of primes, the set of primes, let's call that P. Suppose this is the set of all the primes, union the set of all the perfect powers of integers, not just primes but integers. So n to the power k, n is a natural number and k is something at least 2. Even this set has arbitrarily large gaps, as should be intuitively clear. So this reasoning will prove this statement, and I think if you attack this even with the Chinese remainder theorem, you should be able to find a proof. But anyway, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.